So lesson 2.3 talks about calculating limits using the limit laws. Now the limit laws, you'll notice, are very, very similar to a lot of the laws that we used in algebra, trig. Very, very similar, follow a very similar pattern here. And basically it kind of looks like the distributive property. I wouldn't call it that because what we're doing here is not multiplication. But it resembles that in many ways. So suppose that c is a constant in the limits, the limit of x approaches a of f of x, and then the limit of x approaches a of g of x. So if we take a look at this, we can say that the limit as x approaches a of f of x plus g of x is really the same thing as taking the limit as x approaches a of f of x and then adding that to the limit as x approaches a of g of x. And that works the same way for subtraction. It works the same way when we have a constant here, but notice the constant goes on the outside and we're taking the limit of the function. So this would be c times the function f of x. And therefore, when we have a limit as x approaches a of c times f of x, that's the same thing as c times the limit as x approaches a of f of x here. And then the multiplication, very, very similar to addition and subtraction as well, and division is the same thing. The key thing with division here, though, is you have to remember that you can't have that g of x function, that function in the denominator. The limit as x approaches a of g of x cannot equal 0, because if it does, it's undefined. Okay? And so basically these next two slides just kind of sum up what I talked about. But the names of the rules, we have the sum law, the difference law, the constant multiple law, which was the constant one with c, the product law, and then the quotient law. Okay. And here's an example too. So notice we have two functions here. They're kind of funky looking functions, no pun intended, but we have the function f here, which kind of does this kind of crazy dip. Notice it is a continuous function nonetheless, even though we have a removable discontinuity here. And then we also have the function g, which is discontinuous, right? Because there's a jump here. So if we were to take a look at these values, what we could do is we could say, what is the limit as x approaches 2 from the negative direction? Remember, it's not negative 2, it's as it approaches from the negative direction. So if we're looking at f of x, right, the limit as it approaches is going to be 0, because our value of f of x is 0 right here. And then g of x as we're approaching is going to be, that was g of as we approach 2 right here is going to put us somewhere around like 1.5, you might say. And then over here, as we're approaching it from g, we're at 0. And then that's the same thing, if we're approaching 1, all right, for f of x, the function f of x, we're approaching 1. We notice that we're at 2, all right? And then if we're approaching 1 from g of x, notice that, there's no limit here, because if we're approaching from the left or the right, we're coming to, different conclusions. So it's discontinuous. And then this one right here, g of x, the limit of x as it approaches 2 of g of x. Okay, if we take a look at g of x, we're approaching 2, approaching 2, approaching 2. Notice it's 0 here, which would make this one undefined, right? And so we're going to have our answers to this right now. They're going to go through it for us right now as we go. But this, obviously, it's 1, like we had said. We have negative 1 here times 5, which is going to give us negative 4. All right? These ones are a little bit, more complicated, as we said. But like the left and the right limits aren't equal, so the limit as x approaches 1 of f of x does not exist, right? That's because it's a discontinuity, all right? It's a discontinuous function, okay? Now we're kind of going through some of our laws here one more time. So this is the product law repeatedly with g of x and f of x, and we obtain the following laws. So I think did I skip a little bit? No, these are two new laws here. So we have the limit, and this brings a power into play, right? So if we have the power here, power play, The limit as x approaches a of f of x to the nth power is the same as the limit as x approaches a of f of x, and then raising that entire thing to the nth power. And then the limit of as x approaches a of a constant c just simply equals c. And the limit as x approaches a of x itself is just a, okay? So they're pretty obvious, right? If you take a look at it and you understand what we're talking about with respect to the functions, but you have to, still obviously understand that these laws are also fall true as well. And then we have, our ninth law here, the limit as x approaches a of x to the n equals a to the n, okay? And then this is similar, but the limit as x approaches a of the nth root of x equals the nth root of a, where n is a positive integer. In our 11th law here, the limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. Now, I mean, these two laws right here are obviously, pretty similar, but notice like what's going on here with the roots and with the exponents, and knowing that we are essentially taking the limit of what's within, the root or the parentheses that we're raising the power to, and then we can go ahead and take the root or the power of that of L, as we would call it. Okay. And then we have the direct substitution property as well here. So, I'm going to close up on 2.3. Understanding these theorems, remember, if and only if, it has to approach from both the negative side and the positive side. And let's see here. Okay. And we're going to work on, any types of, example problems that you might have. This is not one that I want to brush by quickly, but the squeeze theorem, sometimes called the sandwich theorem or the pinching theorem, right, is illustrated by this figure right here. It says that if g of x is squeezed between two functions, f of x, notice g of x is between two functions h and f here, right, near a, and if f and h have the same limit, notice they intersect at the same point, then g is forced to have the same limit at L at A, okay? And basically all that means is that this is a point of intersection, and that's the point, and it's sandwiched between it, so we can say that they have the same limit, L at A. Okay. So I'm going to cut it off there, and we'll answer any questions that you might have in our Tuesday, Thursday sessions. Thanks.